Welcome to the training series on ODOT's Benefit Cost Analysis tool for active transportation improvements. This is the final module for our four-part series. This module will cover guidance on walking and biking trip estimation. In this video, we'll discuss the purpose behind trip estimation, key questions to guide how trip estimation is used in benefit cost analyses, and typical data sources you can use to estimate trips on your projects. Lastly, we will show you an example method for an example project. Trip estimation is essential to create any kind of BCA for bicycle and/or pedestrian work. To calculate the benefits of a project, we need to estimate the number of people that will use the project. Those numbers then get plugged into the no-build and build trip variables for the benefit cost analysis tool. Depending on data availability, there are multiple methods that can be used to estimate future active transportation infrastructure use. To begin with, there are four key questions to ask. Who are the people that will be impacted by the new active transportation infrastructure? What are the different ways these people will use the new active transportation infrastructure? Where are these people in relation to the new active transportation infrastructure? And how many of these people are there? Each of these questions are discussed in more detail in the next few slides. There are many ways to estimate trips, largely depending on the type and quality of data available. We will review a few examples here. Census data collection may include information on population, age, employment, or commute data. This may be local, regional, or if unavailable at those levels, national data. Activity data, such as local pedestrian and bicycle counts for similar locations or existing facilities, can inform the number of people that will realistically use the proposed project. Your local metropolitan planning organization or other regional agency likely has a travel demand model that includes trip mode share and trip lengths within the project data. Big data sources may also be useful for estimating the number of people who will use the proposed project by providing estimated trip lengths and volumes based on aggregated cell phone usage data. Large-scale emerging data sources are becoming more common in transportation planning analysis. The Ohio Department of Transportation shares quality data from a variety of sources, including third-party data with other public agencies. For more information on currently available third-party data and other resources, visit the Economic Value of Walkable and Bikeable Ohio webpage, linked below. Lastly, remember to consider future conditions. How many people are projected to live in the region by the end of the analysis period? ODOT's BCA tool includes an assumption about annual trip growth rates. Metropolitan planning organizations or other regional agencies can be a good source of information on local or regional population growth rates and projections to use in the tool. Because local count data and big data sources may not be available or relevant to every scenario, this training covers one approach to trip estimation that relies primarily on census data and is compatible with the BCA tool. Now, let's move on to our key questions. For walking and biking infrastructure, the people most likely to be impacted by a project are those who are located nearby. For this reason, we examine the project's impact area. After selecting an appropriate population data source, defining the project impact area typically includes drawing multiple buffers around the entire project at different distances, such as quarter mile, half mile, 1 mile, or sometimes up to 3 miles. Within each buffer, there will be different assumptions about how many people that live or work within those buffer areas would use the new active transportation infrastructure. For example, a higher percentage of residents can be expected to use the new facility in the quarter-mile buffer area than in the 1-mile buffer area. You should also consider barriers that impact routing, such as rivers, bridges, railroads, and topography. When thinking about the different ways people will use the active transportation infrastructure, there are mainly two groups to consider: people walking and people biking or using other wheeled devices. Assumptions about usage by distance from the facility will differ between these two groups. For instance, someone living within a quarter mile or half mile of the new infrastructure may be willing to walk to it, but someone living 3 miles from the new infrastructure may be less likely to walk to the infrastructure. A person bicycling may tolerate a longer trip to the new facility. In addition to these modal user types, trip types must also be considered. This includes whether people might use the new facility to commute to work or school, to run errands or make other utilitarian trips, and to make recreational trips. For each trip type, the assumptions may differ. Lastly, we will estimate the number of existing and new users differently. Existing users are people that are already walking or biking in the area. Some percentage of these users may be expected to move their trips to the new active transportation infrastructure. New users are people who were not previously walking or biking but would be expected to shift modes or begin walking or biking because of the new active transportation infrastructure. There are different formulas we will demonstrate to estimate the percentage of residents who would use the new active transportation infrastructure based on whether they are existing or new users. To decide how many people will use the new active transportation infrastructure, first we have to know how many people live near the new infrastructure and how likely they are to use it. This starts with census population data. For bicycling, there is a detailed NCHRP report titled Guidelines for Analysis of Investments in Bicycle Facilities that provides research-backed equations for estimating potential new bicycle trips based on a person's home distance from the infrastructure. This document has different approaches to estimating trips within 400, 800, or 1600 meters, approximately a quarter mile, half mile, and 1 mile, of the new active transportation infrastructure. According to the NCHRP methodology, within a 400-meter buffer of the new facility, the number of new users is potentially 1.93 times that of existing bicyclists within the area, nearly tripling the number of users. At 800 meters, the factor is 1.11 times the existing bicyclists within the area, and at 1600 meters, the factor is 0.39 times the existing bicyclists within the area. This type of scaled approach, where the anticipated number of new users that are very close to the infrastructure is high, and tapers off as you move farther from the project, can be adjusted depending on local conditions and applied to people walking using different distance assumptions. Note that the methodology demonstrated in this training is based on an expectation of usage by nearby residents. There may be some cases where we expect people walking and biking to primarily be visitors or customers at businesses, where this method may not be appropriate. Determining how many people to include starts by calculating the number of residents within an area and applying factors to narrow down this number to a realistic estimate of people who would walk or bike along the new active transportation infrastructure. This can be done by looking at census data for population, journey to work mode used, and the percentage of the population that are workers over the age of 16, potential commuters, or the population over 18, potential adult pedestrians or bicyclists. Using these sources, follow the equations on the slide as found in the NCHRP report. To get the number of daily existing bicycle commuters, multiply the number of residents in the buffer area by the regional bicycle commute share. Multiply again by 0.4, which in this case is the assumed percentage of residents who are adults, multiplied by the assumed percentage of adults who are commuters. To calculate the number of total daily existing adult cyclists, follow a similar logic using the equation on the right. In this equation, the adult bicycling rate is a separate formula which stems from the NCHRP research about the approximate percentage of the adult population that bicycles. That calculation is shown in blue and relies on the region's bicycle commute share. Let's walk through the trip estimation process for an example project that fills a 4.5-mile trail gap. While this is a real trail gap in Ohio along the Great American Rail Trail, this trip estimation was conducted for this training video and not part of an existing proposed project. For this example, we'll use guidance from the NCHRP Report 552, Guidelines for Analyzing the Benefits and Costs of Bicycle Facilities, as well as real census data and example trail counts. We'll start by determining the number of residents within our impact area. To determine the impact area population, we'll begin by using GIS to map the project itself and 3 buffer areas: 400 meters, which is about a quarter mile, 800 meters, which is about a half mile, and 1600 meters, or about 1 mile. These buffers were selected based on the guidance in the NCHRP report, which found that people closer to bike facilities are more likely to bike than people living farther away. The next step is to map the census data. Pick a geography that works for you. For this example, we've used census tracts. In other instances, block groups or blocks could be used. This is where context and judgment begins to factor in. Evaluate the relationship between the census tracts and the buffer areas and set an approach for determining which census tracts are part of the impact area, and how the impact area census tracts will be divvied up based on the distance buffers. For our example, the first approach for determining impact area census tracts was to include all census tracts that touch any part of the 3 buffers, as measured using crow flies distance in GIS. But based on the shape and size of some of the census tracts, that would mean there were people over 3 miles from the project included in the impact area, which didn't seem generally defensible for a BCA. However, this project is filling a gap in an existing network. There are people in the potential impact area census tracts that are 2.5 miles from the project terminus, but only 3/4 of a mile from an existing facility that connects directly into the project. So, we opted to use data on the existing bike network to inform the identification of impact area census tracts. We used GIS to identify the centroid of each census tract. The following guidelines were followed for determining the impact area. All census tracts with their centroid inside the 1,600-meter buffer were included, and all census tracts with a border touching the 1,600-meter buffer and that have a centroid within 1 mile of the existing facility connecting directly into the project were included. The census tracts within the impact area are shown in darker blue. The next step was determining which census tracts fall into each buffer area. The first approach was to use centroids, but based on the context of this project, there are no census tract centroids within the 400-meter buffer. So, a different approach was identified. Using GIS analysis, we opted for the following methodology. Any census tract with a border touching the 400-meter buffer is included within the 400-meter area. Any census tract with a border touching the 800-meter buffer and the 1,600-meter buffer is included in the 800-meter area. And any census tract with a border touching only the 1,600-meter buffer is included in the 1,600-meter area. With that approach, we can use the census tract data to calculate population within each of our buffer areas, which we'll use for the next steps of trip estimation. Now that the project impact area has been defined, the next few slides will cover how we estimate the number of existing adult cyclists, both commuters and non-commuter or recreational riders. Let's start by calculating the number of daily existing bicycle commuters using the formula we introduced earlier from the NCHRP document. As you can see, R represents the number of residents within the buffer areas. C represents the regional commute share. That's where we plug in some census data about the percentage of adult workers who bike to work. In the county where the project is located, about 0.4% of commuters travel to work by bicycle. And you'll recall that 0.4 is the assumed percentage of residents who are adults, multiplied by the assumed percentage of adults who are commuters. If more accurate local data were available, you could substitute this. When we complete the equation for each buffer area, we get an estimate of existing daily bike commuters, which totals 84 people in this example. Now, let's calculate the total daily existing non-commuter adult cyclists. We'll start with the same R values, then plug in a value for T, which is the adult bicycling rate. The guidelines for analyzing the benefits and costs of bicycle facilities methodology provides another formula for us to calculate T based on C, which is the commute share we used on the previous slide. Based on the context of this project, we have selected the formula for a moderate adult bicycling rate. This is based on the overall mileage of the regional trail system near our project. There are also formulas available for project contexts with low or high estimated adult bicycling rates. The context of your project and the surrounding area should guide which formula you use. For our example, the value of T is 0.8%. The final part of the daily existing adult cyclist formula is 80%, which is the researcher's estimation of the percentage of the population that are adults. Again, you could use local data to refine this assumption if available. When we complete the equation for each buffer area, we get an estimate of existing daily non-commuter cyclists, which is 369 people in this example. Now that we have quantified existing adult cyclists in the impact area, the next few slides will cover trip estimation for new cyclists. Using the identified numbers of existing commuters, we can estimate the number of new commuter cyclists using a formula from the Guidelines for Analyzing the Benefits and Costs of Bicycle Facilities. Start with existing commuters for each buffer area, and increase by the multiplier identified and provided in the report by researchers based on the buffer distances. The multiplier factors in how people who are closer to the bikeway are more likely to use it than people located further away. With some simple math, we now have the number of new bicycle commuters in our example, 97. To estimate the number of non-commuter daily cyclists, we do pretty much the same thing, only using existing non-commuter daily cyclist numbers. The same multipliers are used for each of the buffer distances. In our example, we used the formula to get a sum of 428 new non-commuter adult cyclists. The table shown summarizes the bicycle trip estimations we just walked through for this example. Using this method, we've calculated 453 existing adult cyclists and 526 new adult cyclists. The next step is to estimate the number of existing and new pedestrian trips in the project impact area, and then we should have what is needed to begin quantifying benefits. Unlike with cyclists, there is no established methodology for determining the number of existing and new pedestrians. Many approaches could be taken, but for this example we've used one based on bicycle and pedestrian trail count data. Let's assume that the county or region in which the project is located has 3 months of bicycle and pedestrian count data available from June through August for a 4-mile segment of trail that is in a similar context as our proposed project. These counts should be within a reasonable time period of proposed project construction. Let's say they are from 2023. The number of existing and new pedestrians can be calculated based on the assumption that usage of the proposed project will reflect the same mode split as the 2023 count data. Therefore, the number of existing and new adult pedestrians can be calculated based on the number of existing and new cyclists. In our example, the average percentage of total trips made by cyclists was 66%, and the average percent of trips made by pedestrians was 32%. The remaining 2% of trips were made by other modes like roller skating. Using those percentages, we can extrapolate the number of existing and new pedestrians using the equations shown on the slide. By dividing the number of existing, shown on the left, or new, shown on the right, cyclists, by the percentage of total trips made by bicycle, we get the total number of facility users. Then we multiply that by 32% to get just the pedestrian numbers. In our example, we get 219 existing adult pedestrians and 255 new adult pedestrians. And with that, we have estimated existing and new trips for our example Great American Rail Trail GAP project, and are ready to plug these numbers into formulas that quantify benefits like safety, recreation, health, etc. Through this methodology, we've identified 453 total existing adult cyclists, 84 commuters, and 369 non-commuters, 526 total new adult cyclists, 97 commuters and 428 non-commuters, 219 existing adult pedestrians, and 255 new adult pedestrians for a total of 1,452 estimated daily users of this proposed facility. In a typical BCA, this data would be plugged into an annual estimation formula to count the number of trips expected annually and to be the basis of calculating per-trip benefits related to safety, health, or other benefits. The number of trips could be expected to grow from this baseline given regional population estimates or other factors. If we were to use the ODOT BCA tool for our example project, this is how we would plug it into the trip estimation results. 219 goes into box 3.01 as the average number of walking trips per day in the no-build scenario, which is the number of existing pedestrian trips we calculated. In box 3.02, we add both existing and new pedestrian trips as the average number of walking trips per day in the build scenario, which is 474. For cyclists, we input the average number of cycling trips per day in the no-build scenario as 453 into box 4.01. And in box 4.02, we input 978 to represent the average number of cycling trips per day in the build scenario. This wraps up Module 4, Trip Estimation, and this is the end of our training series. Thanks for watching! We hope you found these videos helpful for your benefit cost or project analyses.